Start the recording then, why not? 12:31, that's like early for us, give or take. So welcome back, happy Thursday. Happy Garbage Day to those of you who are celebrating elsewhere. We have piecewise models to talk about, but I wanted to ask first if there's any homework questions. The next one is due Monday, I think, if memory serves. That sound right? Yeah?
I thought it was Wednesday, and I was checking the schedule, and then like, okay, Monday, okay.
Yeah, so I want it to be on Mondays as like a general rule, but then if we get behind a class, then I move it to Wednesdays. But because we finished the quadratic stuff last week, I feel like Monday is a reasonable goal. But yeah, Monday in theory. Any questions on that right now? Looking at the chat, looking at the faces? Not yet? Not yet. Okay, that's fine. That is fine. The next one after this, by the way, will be a piecewise one. So you'll get a chance to practice these models as well. All right, so what are piecewise models for? Let's start there.
They're good at modeling individual participant data when you have distinct phases within the data collection.
Distinct phases within the protocol or
Okay, yeah.
time series would be another word for
Okay.
it. Mm-hmm. Yeah. So then, can you give me an example of when you might use something like this?
Yeah, so as an example, you might be utilizing a treatment under a behavioral treatment, while on a medication, and then you might want to see how the behavioral treatment does in isolation. So you take the individual off the medication, still keep that behavioral treatment in place. So that'd be your first line, and then maybe you want to go back, reverse back to see how that looks. So you put them back on the medication, go for a bit, and then take them off again. So new line, and then take them off and just keep that behavioral treatment in. Suppose if you even wanted to get fancier, you could also look at med-only conditions and nothing as a true baseline in there and have like a A, B, C, D thing. Sorry,
Yeah, you
I
could
went
get
down
fancy.
like a deep rabbit hole there.
So let me repeat that for the recording and for the Zoomers. The example was if you're doing a behavioral treatment and you want to examine the effect of introducing or removing medication, then you might have, a change point when you start the meds, another change point when you get off the meds, and so forth. Not point and change point and break point, those are the terms. You can use those interchangeably. That refers to like where the pieces break apart. Let's see, you had one, I think, too, right? Rebecca? An example of when you would want to do this?
So there have been studies done in language assessment for like test prep classes that have found that there are distinct benefits to just taking one practice test. And so, for example, a study done in 2017 had 3 groups. They had some people who had no practice, no class, one that just took a practice test, and one that had a whole semester as test prep. And there was no significant difference between the last 2 groups. But it would be really cool to do a study where you actually follow people in the class over the span of the class to see if they benefit most at the very beginning and then if it drops off at the end.
Yes, so another example of whether more test prep is beneficial. So after the first example, like that could be one piece, is just do it once, and then after that you can look at the extent of diminishing returns, further practice. Yeah. Let's see, Zoomers, do you have any examples of when you might choose piecewise models? Okay, 10?
So I do a lot of work with financial aid, and different administrations. You can kind of see like trends in financial aid. The 2008 recession also was like a break point in terms of like aid, all that sort of stuff. The pandemic is a not point. So if you're trying to do, I don't know, let's say financial aid over the last 20 years, it gets a little complicated.
Indeed. Yes, good examples. Others? Roomers or Zoomers? Anyone? So to reiterate, the models that I'm showing you are sort of like the starter kit for these things. They are the simplest version, and they assume that you know where the knot should be based on your design or your hypotheses. There are other versions that their job is to approximate nonlinear functions and find where the breakpoints are and how many are needed. So that is something that can be searched for if you're interested in that version of it. Another example, anything refugee related after the Muslim ban. Yes, so laws going into effect and the effect of changing policy and procedures like that. Yes, another great example. Go ahead.
Kind of related to that last part you said, if I heard you right, you can run a program to look to see if it finds the breakpoint if it's not pre-specified.
Yes, you can turn the location of the breakpoint or points into a model parameter to be maximized by the same likelihood as everything else.
Gotcha. So could you say do that analysis even if you like know where the breakpoint is already, and then see if like where that is matches with like actually what the data say?
Yeah, you could. That would be basically a nested model comparison, I think, where you treat the parameter as known, or you try to estimate it, and you can see how close you are, and you can see what if you know it, then it should fit, not worse than letting it figure out where it wants to be.
Yeah, so I can just think of some data where that would be like very interesting. Like, you know, this thing should have happened at this point, but like data-wise.
Yeah, so that you can check on your intuitions as to when processes should have a discrete shift or discontinuity, as they sometimes call it. So yeah, so those are more advanced models. They require usually different software estimation, so something that you can sort of write your own version of the model. Like SAS NL mixed is what I've used to do those kinds of things before. M+ also, if you can coax it into an SEM framework. So, but this will get you started at least in thinking about these as possibilities. So in our class, this is the version that we're doing. So should we go back over this? Re-go over or just review? Any votes? Okay, 2 votes for review. All right. So my example is this one here. So this is the answer key, so to speak. This is the plot that illustrates the saturated means model. So these are the means that are best for each occasion in this data set. The question is, how can we make a function that's going to approximate them so that we can examine individual differences in the aspects of the function over time? So I did this completely atheoretical thing based on literally what it looks like. There's an early practice effect, so this would be analogous to taking the test once, for instance. And there's a later practice effect, and just visually it looks like the slope is shallower. That's a hard one after this. So there's different ways to parameterize these models. I want to show you 2 variations. I'm sure there's more, but which one you pick is usually based on what you might want to know about your data. So this one, I call this 2 direct slopes. This is going to tell you whether or not there is change during each period. That's the objective of this model. So the coding scheme is shown here on the bottom. The first predictor would go from 0 to 1 to indicate the amount of time that has passed relative to the intercept at the first occasion, but then it stops at 1 to essentially shut off. And so the dotted line here would say what would happen if nothing else was in the model. Then purple picks up where orange left off, and it tracks the further change from the breakpoint at session 2. So that's why it starts at 1 at 3, because 3 is 1 more than 2, which is like its reference point. So internally, this is relative to the breakpoint. So this model is advantageous if what you want to know is whether or not there is change on average during each time period. Question? No?
Not formulated yet.
Not formulated yet. Okay. An alternative version replaces the orange predictor. So purple stays the exact same, and the orange one turns into what we last week called linear time. It still is. So this one is parameterizing what happens differentially in the second period, whether there's differential change. Let me get out, I'm going to do some drawing with paint. I haven't done that in a while. I know. I'm not cool enough to like use my pen on an iPad like other people, but I am cool enough to get out paint. Let's see, crayon maybe? Yeah, it's always the spray paint one. No, I don't want the crayon one. Something like that. That's better. Okay, here's my y-axis, my x-axis, all right. So let's say that you are in a intervention design within a school setting. So like here's the beginning of the school year and here's the end of the school year. And in terms of measuring something like, let's go with words per minute, reading fluency, something like that. If you did nothing different, just the effect of school, hopefully they're growing from the beginning of the year to the other part of the year. But let's say that you're interested in comparing what happens before and after some treatment, where you change what you're doing in the classroom. Well, given that they're supposed to be growing the whole time, like let's say that this is where things change, the model that is set up to tell you whether or not there is change during each period, so the first version here, 2 slopes, that model is not going to be useful because of course they're going to change during the second part and the first part. Like that's called school. What you'd want to know is like if this were a control condition and you have a treatment condition maybe that's on the same path, do they change more? Like if that's what you want to know is differential change, then the second version of the model is going to tell you that directly, instead. So I call this slope and deviation slope because purple is going to tell you how different the slope is after the knot point. And that is also a direct test as to whether you need a piecewise model in the first place. Because if the slope for the purple predictor here is not significant, that means linear is sufficient for the whole thing and you don't need 2 different slopes. So you can have a more parsimonious model by just having the one. All right, how's that sit with folks? I think that's as far as we got. Okay, any questions? See a few thumbs. Yes, have you formulated now?
I think so.
Okay.
So, with the orange one, the dotted line here, so we're saying that without that breakpoint, we're assuming it's just going down?
Yes, so if the purple predictor were not in the model, this would just be a linear time trend.
And it's just going down?
And it would, yes.
And so, is this just for like the purposes of an example, or like would it always go down? Could it like go straight at that point too?
In terms of the direction of the slope, that would be estimated for the data. So down
Okay.
is not a requirement.
Okay,
I was
all
just, in the context of this curve,
Yep,
like this is what
yep,
I was
okay.
trying to draw.
I just wanted to make sure I was understanding that it could be any, it just, for the purposes of the example, that's the way it's going.
Yeah,
Okay.
so
Awesome.
like if you only had the purple predictor in the model, then this is the trajectory. Like it lumps the first 2 occasions together.
Yeah.
So orange then, after controlling for purple, becomes just the trajectory for the first part. So this is one where through the process of isolating unique effects, the interpretation changes. So we'll see that as well. In terms of setting up these models, I wanted to do just a little bit of practice with the logic of that. So Excel instead. So session is our original variable. We have 6 of those. What if I wanted to put the intercept at the knot point? Could I do that? Sure, and that's actually easier, I think, to think about it that way. So if we have slope 1, we'll call that slope 1, 2, and slope 2, 6, for instance. We can do the direct version of the model. So if I want the intercept at session 2, that means I zero out those 2 occasions. If I want the first slope to track the change from 1 to 2, what would go here? -1, yes. And why do you say that?
Because 1 is -1 less than 2.
Yes. Because 1 is 1 less than 2, yes. Now what would go here then if the intent is for this slope to capture only the change from 1 to 2? You got 2 choices. It's either 1 or 0. We'll do it. 1 vote for 1. We got 2 votes for 0.
Well, Maybe it's in the other column, that's where the one should go.
Yes.
Okay.
So this one, these are zeros because the idea is that it leaves off where time ended, whatever that is in your coding scheme.
Yep.
So if this were a 1, then it would keep going through session 3, and that's not our intent. So then over here, what goes here? Yeah, it's not awake yet. What goes here? 1. Yeah. So then this is the change relative to the not point of 2.
When you say not point, it's KNOT, right?
Yes. Breakpoint, change point, not point. Yeah, I don't know where the term not point comes from, but maybe if you like visualize a little knot. Yep. So these, like, honestly, whenever I have to set up a model like this is the first thing I do is I build a table like this for myself, and then I try to figure out how to write the code that would implement the table. So I will give you, in your homework, you will have a 3-piece model. Homework 5 is the most challenging one. They're like, what? It's based on a true story, too. Like, no, it'll be okay. It'll be okay. I promise. And we can go over stuff in class, too, for it. It'll be fine, but. All right. So I will show you then in the example both versions of these models. So the direct slopes version, just to summarize what I said here, fixed intercept is still going to be the expected outcome when both of your slopes predictors are 0. So that's up to you to set that up. And then the first one would tell me whether or not there's change initially. The second one would tell me whether or not there's change after that, the rate per session in this case. And then the random effects would have the same corresponding interpretations. So the intercept gives you individual differences at a particular point in time. It's up to you where that is. You can choose which one you're most interested in. The first random slope would give you individual differences in the change from 1 to 2. And the second random slope would give you individual differences in the change from 2 to 6. So this is, everything is just relative to 0 as a reference point. Is there change, and does it vary across people? So then the other version of the model, the deviation slope version, has a different interpretation, both with respect to the fixed effects and the random effects. The first slope ends up being the same, even though it's based on a different variable. Because after you control for the second slope, the first one uniquely indexes the change from 1 to 2. So the fixed slope would tell you the change on average from 1 to 2. The random slope variance would tell you about individual differences in the change from 1 to 2. Then the second one, the deviation slope, tells you the difference in change, whether the change grew after the not point or shrunk, as it were. So that means the random slope variance then tells you individual differences in the extent to which there's differential change. Now, that's a hard sentence, I know. I'll say it again. Individual differences in the extent of differential change. So it's relative to what would be expected based on the change that already happened. Like relative to that. So back to this picture, right? The question isn't, are they changing after the intervention? It's, are they changing more relative to what is expected? If this is my expected trajectory, then how much more is this slope afterwards in this group? And then are some kids like this, some kids like this? So individual differences in the extent of differential change. That's the idea. So if you have everything have a fixed and random effect, these models are likelihood equivalent. They're just rearrangements of each other. So you can pick which one is more convenient for what you want to know. In that sense. Yes, okay. Do you want to see an example? A question, relative to their own expected change or the average expected change. It's relative, so relative to the fixed effect is always the case. The question is, what does the fixed effect mean? The fixed effect in the deviation slope model would be differential change from the first slope. I think numbers will help us. I think numbers will help us with an example. So I'll walk you through both sets of models, and in the process we can practice thinking about fixed and random effects some more. How's that? Why not? So same data as before, 6 sessions, older adults, that we are expecting response times to decline as a function of extended practice. So the same data set as we had in example 6a. I do not know a more parsimonious way to do this in Stata, so if any of you do, please let me know. But I had to create each slope manually by saying, if it's this session, then make this new variable this. So I started with a variable that had just the session in it and then recoded it in this case. And then, so I have the coding scheme here is the first one, 0, 1, 1, 1. So that's going to make the first slope shut off at session 2. 0, 0, 1, 2, 3, 4 then has the second one pick up after session 2. So this is the original version of the two slopes model. I also made time in here so that I could show you what happens when we switch the first predictor to be that one. We are going to do tests of absolute fit again via Wald test by adding in the extra deviations to the trajectory to test if they're significant. And note that I only have 3 here for the second trajectory. That's because the first one is saturated. The change from 1 to 2 is going to be perfectly captured by that slope no matter what. So it's the second one that I'm worried about. And R, folks, I didn't want to leave you out. So here's my coding to create the new piecewise slopes using these integers. I'm sure there's a more efficient way to do it, but this way has the advantage of being transparent as well. So any questions on the setup to build these new time-related predictors for your slopes? Fairly straightforward once you know what your pattern is, what your objective is. That's the hard part, I think. So then, here's an example model. So if I can get everything on the same page here. So this is to remind you these are the two predictors that we're using in this. So at this point, I only have 2 fixed slopes. I have no random slopes. So in the polynomial models, I started with fixed linear, then random linear, then I added the quadratic on each side of the model. These 2 slopes go in at the same time, otherwise they don't create the pattern that I want. So this is not a hierarchical model with respect to which comes first, the way that polynomials are with time and time squared. So I have 2 fixed slopes, 1 random intercept at this point. That means that I'm allowing for a broken stick type trajectory, but it's assumed to be parallel across people, only a random intercept at this point. That's my starting point. So this model is going to allow me to answer the question, is there change from 1 to 2 on average, and is there change from 2 to 6 on average? Linear change in both pieces. So we have slope 1, 2 and slope 2, 6 here. The usual stuff after that, I am storing the results of the model so if I can calculate effect sizes and that kind of stuff. I had a question the other day about this in here. These are L's, not 1s. It's very difficult to tell the difference, but it stands for log likelihood. And so this is a saved result that you can access. And so I have it here, Act 2, so that you can get your -2 log likelihood and not have to compute it. Next step, I am doing this the long way for pedagogical purposes rather than using margins to get predicted outcomes at each occasion. So the times 1, by the way, you don't have to type that. Obviously, it's just 1, but I'm doing that so that the coefficients match what it looks like in other packages, like the column of 1s here for the intercept in R. I'm putting the 1 in Stata to make that analogy, and SAS has the same requirement of putting a 1 in. Then after that, note the values here are exactly like they were in my table. So however you set up your pieces, those are the same values you would multiply your slope coefficients with to get the predicted outcome at each occasion. So note, I'm calling these intercepts. I could also call them conditional means, expected means, predicted means. But this is if this is the intercept at session 1 is what's given by the model, then I can ask for what it would be at any other occasion as a linear combination. Then I had already ran an empty model, so I have the results from that saved here to do a pseudo R-square. So given that I have these 2 time slopes, which variance should be reduced? Random intercept or residual? Relative to an empty model with no predictors, which one should have been reduced? Now we got 1 vote for random intercept, we got 1 vote for residual. Got 2 votes for random intercept. 3 votes for random intercept. So I'm talking about these two slope predictors right here. Let me ask it a different way. Are these time-related variables or people-related variables? Time. So should they predict people variance or time variance? Yeah, residual. Yeah. So what will happen if these two slopes contribute to the model, then the residual variance will be reduced, and because of that, the random intercept variance will increase a little bit. That's confusing that they're in level 2. I know. They have their own equation at level 2 because potentially each person can have their own version of this. But the actual variables themselves are in the level 1 equation. So in general, in these models, the predictors that you add explain the variance term that is in its own equation. So like these ones are in the level 1 equation, they'll explain E. When we get predictors in the level 2 equations, they'll explain each of the corresponding U's. But that's the last unit in class. So yes, residual should be what is explained by adding these two fixed slopes related to time. And then in R, I am keeping this same option, by the way. It doesn't hurt anything, and I found that it matches SAS and Stata better. So that's the reason that I'm picking it. There's none other than that. I have my two fixed slopes in here, only one random intercept. And I have our output, it looks like, this time. So I'm going back and forth so that I don't end up duplicating too many results. Labeled a few things in here, so just as a reminder, deviance in Elmer is where your -2 log likelihood value is. AIC and BIC and the other stuff as well. Random intercept variance, so this is, the outcome is response time in milliseconds. That's why these numbers are so big. So intercept variance of 202,000 and some odd. Here's my E variance. And then each of my 3 fixed effects. So let's walk through these for a second. Intercept tells me what? 1961 milliseconds means what? It's
practice.
Yeah, response time. Response time is the outcome.
So it took that many.
Is our intercept at session 1 or session 2?
Intercept is at session 1. So yes, session 1 is time 0. So this is my session 1 predicted response time. So almost 2 seconds the first time they do this task is what it takes on average. Then the first one, slope 1, 2 is just a difference because there's only 2, it going from one occasion to the next one. So the second occasion was 163 milliseconds faster. That's what we know. And p-value is 0 to 12 decimal places. So yeah, it looks like that. We'll call that significant. Slope 2.6 then is a linear slope.
Decreases by 32, 33,
Yep.
for each further.
For each session, yes. So response time after session 2 decreases by 33 milliseconds per session. So this is a rate, not just a difference. And that is significant as well. So these slopes are testing against 0 for no change, how much change there is, just like we're used to seeing in any kind of standard slope. The R code to get these predicted means per occasion, I'm using contest 1D, that's from the Elmer test package, and the numbers here, the 1 is for the fixed intercept because we always need that in creating a predicted outcome. And then the other values in here are based on the coding of my slopes. So they match exactly my table. And there's one more thing in here that I might want to know about, which is right here. Can you tell based on the numbers what I'm asking? There's a minus sign in here. Minus signs create subtraction instead of addition. Difference between the two slopes. Yes, indeed. That's what the label says too. So I'm asking, do I even need 2 slopes or is 1 enough? The difference between them is not a model parameter, but it's a linear combination. And the corresponding Stata code would be this one right here. So I wrote it in the same order to match. So the question I'm answering is whether or not there's a difference between slopes. It has nothing to do with the intercept. That's why the constant part is not here. So in general, if you're not predicting the outcome, you don't need the intercept in these equations. You just need the slopes that are relevant. Question?
Yeah, so could you go down just a bit to the, awesome. So with the slope 2-6 piece,
Mhm.
so we're working with, 6 sessions here, 6
Yes.
time points. So what happens when we have like, say 100 sessions per individual or even more? So like right now with, the slope 2-6, it's showing that we're decreasing by that amount every time. But presumably if we had more sessions, you're only going to get faster to a certain point, so it would level off.
Right.
In that case where we have like more sessions, is there a way to model and account for like, within these sessions, this is where you're going to see the most change or the most increase, decrease, whatever it is, and then for the rest, you've probably like leveled off?
Mhm.
Because I would hate, potentially like for an effect that is effective to be like masked just by averaging it out across, a bunch of sessions.
Yes.
If that makes sense.
Yes, it is. So the question was, there's only 6 sessions here, so a linear slope that implies change is going to keep happening is maybe reasonable. If there's 100 sessions, that's not going to be the case. So what you want, I think, I actually have a picture. I didn't know you were going to ask this question, but I have the answer. Like, if you have a function that looks like this is 30,
Yes.
30 sessions of practice. So you don't want a line to predict that response time is going to improve indefinitely into negative territory. So I think the issue that you're asking about is whether a linear slope is a good idea if you have 100 occasions, and it's not.
Yeah.
I think you need a different kind of function within that piece.
Yep.
So it's like this is introducing the blue line. This is the fit of a negative exponential model. And this model, one of the parameters that it has is an asymptote, which is your optimal level of performance, like if you followed the curve to infinity.
Mhm.
So that's what I would the same concepts in terms of like start with the means, see what the pattern looks like, figure out a function that would fit that pattern, would apply within a section of your time as opposed to just the whole thing.
Okay.
Same ideas.
Love this class.
Woohoo!
So the easiest way to figure out, Alex,
Yeah.
the next question is to just draw the plot first, so to figure out what's happening.
Yeah, so the question is, how do we get the means? You can always compute means, okay? Like any software package, no matter how small your sample, will compute a mean. And if it's a single case design, it's one data point, right? It's not a mean. But in these models, the saturated means model is not going to return the arithmetic means if you don't have complete data. They're not going to be the same. The maximum likelihood estimator is trying to recreate the means that would have been there had you had complete data, under an assumption of missing at random. So basically, the way I think about it is like you have this multidimensional likelihood mountain, where it's as many dimensions as you have variance components that have to get found. And the assumption is that the shape of the mountain would be the same whether or not you have all the points to it. Like, it's trying to recreate the shape and not the individual values within it. Craig Enders, is that book on your reading list this semester? It probably is. Chapter 4 in that book. I think 3 introduces maximum likelihood, 4 introduces missing data and maximum likelihood. I would refer you to that source because he explains things very clearly. Also, next semester, Jonathan is teaching a seminar on missing data. So I would encourage you to register early. I think that one is going to fill up because apparently there's nothing else on campus that touches some of that stuff. So missing data is a very tricky topic. But where I was going with this, if you have missing data and it's not a single case design, then the observed means are going to be biased by whatever missing data most likely, because if people don't come back for reasons, then like the mean of who's left is not a random subsample of the mean that you started with in terms of the population. So there's different reasons for missingness. The saturated means model is supposed to fix that. But if you're thinking of this as a single case design, then you can just literally plot the data and see what it looks like. So does that answer your question? Okay, so saturated means if possible, but means if not. So I don't like the fact that I don't know how to table these things neatly together. I'm not good enough at R for that, so I just spit out the table from SAS and put it in here so you could see all the values next to each other. So the difference between, so here's the 1961 we saw as the intercept. And by the way, out here, I have labeled how these numbers came to be so that you can map those numbers back onto the parameters. So then the second occasion is less by our slope of 163. And then after that, you can see that the predicted means are declining by 33 milliseconds a session. And that is creating this pattern right here. So the blue line is the fit of this model. So we have the intercept is correctly on session 1 here, because this first part is going to fit nearly perfectly. And then this one is covering the rest of it. So we have 1962 minus 164 minus 33 as our function. Now, I told you earlier that it looks like the second one is shallower than the first, right? That's the last piece of information that we would want to ask this model about. 130. That is the slope difference. So the second slope is less negative by 130. That's how I would say that. The rate of change has slowed down by 130 milliseconds a session.
So is that the same as the slope and deviation slope model, or is that different?
That's what, yep. Yeah, so there's 3 pieces of information. Is there change in the first part? Is there change in the second part? And is there differential change between the two? Any one model is going to give you 2 out of the 3, and the third is a linear combination.
Okay.
So yep, that coefficient of 130, that's going to show up in our deviation slope model as the second slope's slope. Yes, indeed. And these 2 piecewise slopes explain 24% of the level 1 residual variance. This is Jonathan's function pseudo R-squaredinator that I'm using for this. So it takes as input the smaller model without the parameter you're trying to compute an effect size for, and then the larger model is the one that has it in it. And as I had expected, the intercept variance increased just a little bit. That's why pseudo R-square is negative, because it is tied to the estimation of it using the residual variance as the correction factor. So that is an expected result as well. Okay, how are we doing? Okay, so these are parallel trajectories, right? Do you think people might improve at different rates?
Yeah.
Yeah, most likely. Empirical question. So this model then introduces one new random slope. I pick the first one. That's an arbitrary choice. So these models are not hierarchical. I still like the idea of adding the random slopes one at a time, because if you add them all at once, you don't know which one is really doing the driving. I picked the first one arbitrarily, but also thinking about the most of the change is happening here. So I would expect maybe the most individual differences, because that's where the most of the action is. How many parameters have I added to my model? 1 vote for 2, 2 votes for 2. Yeah, it's 2. It is 2, because I've added not just the variance of U1 as my random slope, but also its covariance with U0, and that's not in the scalar equations like this. So in order to do that, in Stata, I have slope 1, 2 here, so there's an implicit intercept after this that I don't have to write, and along with it, you would want to make sure you ask for the covariance between the two. So that's what covariance unstructured refers to. That is the G matrix in Stata. The R matrix is still independent via the residuals option, and technically you don't even need to write this, but I do for transparency's sake. So the fixed effects are pretty much the same. The new part here, so this is Stata output instead. Note that it puts the random slope variance first and then the variance of the intercept. So this is slightly out of order relative to what you might expect, and then they stick the covariance at the bottom. And let's see, residual variance is here. So how do we know if we need to keep our random slope? If it helps. The confidence interval doesn't overlap 0. Is that good enough? Not in my book.
Probably not.
Yeah. Pun intended, not in my book. Ba-doom-tsh. Likelihood ratio test for the win, yes. Can I just use this one since it already did it for me? Nope. This one, 3 degrees of freedom, is because it's testing the entire G matrix, whether you need any random effects. That's what this is testing. So this is only useful in the case where you have a random intercept, and that's the single thing that you want to know if you need. Yep. SStat recovariance relevel with your person ID, and then the key phrase correlation gives you the correlation between the intercept and slope instead. So up here it's given as a covariance in Stata, and it's given as a correlation here. Also, here is the V matrix and the V core matrix. So I printed it from R actually because it's using scientific notation still. Now this is an interesting pattern. I have one variance here, a different variance here, and then the variance is constant after that point. Likewise, I have one covariance between occasions 1 and 2, but then after that, it's constant. So is this a coincidence or a consequence of our model? Consequence.
The extra step is the residual variance, right?
The extra stuff?
Like the covariances outside that are constant?
This is the predicted V matrix across all the occasions, so the residual variance goes into it, if that's what you're asking.
Like the ones where the covariances are constant, that's just the residual variance.
No,
No, oh,
no, these are, would be due to random intercept variance, but
okay.
not just due. Yeah, so it is a consequence. Why does this pattern look like this? Like, a bunch of it's the same and then part of it's different? Because of our coding? Yeah. What about it?
We kept it at 0.
Well, we have one random slope, right? And this random slope governs the change between 1 and 2 only.
Mhm.
Yeah, slope 2, 6 does not yet have a random slope. So essentially, after time 2, you have compound symmetry.
Well, that's what I was trying to say.
Yes, random slope variance is only for 1 and 2. So that part has non-constant variance and covariance, but the rest of it is constant. So it's like half compound symmetry. Here's the corresponding correlations, and you can see this a little more clearly. The expected correlation of occasion 1 with the others is this much, but then after that, it's one number. Because after 2, it's a random intercept model. So that creates a little bit of weirdness, I think. It's not a realistic model from that perspective. Likelihood ratio test says yes, we should keep it. So let's fix that problem and estimate random slope 2, 6 as the next stop. So there's the corresponding R code, by the way. So we add the second U. Now how many parameters have I added? By adding in U2 here. 2 votes for 3, 3 votes for 3, 4 votes for 3. Yes, indeed. Because we add the variance of U2 and the covariance with the random effects that are already there at level 2. So what's the word I want? I'm having more word finding problems today, my goodness. It's a trick that you use to remember something. Mnemonic?
Mnemonic.
There we go, came up with it. My mnemonic for this is look at how many U's there are, and that's how many new parameters you just added. So if you don't have any U's and you add a random intercept, that's 1. Once you add the second U, that's a change of 2. The third U is a change of 3, and the fourth U will be a change of 4. Yeah. So this model says there are 3 different ways that people differ from each other. There are 3 sources of person dependency. Something that is constant over time, that's the intercept, and then these sources that have to do with individual differences in change that introduce heterogeneity of variance and covariance across each of these sections of time. So now we can ask whether people differ in change during the second period from 2 to 6. Stata code looks very much the same. The only thing that I'm adding is we're going to do some confidence intervals, so I added code for that. So I saved first the 3 fixed effects, and then I saved and variancified these things. So Stata saves this as the log of the standard deviation. This code turns those back into variances. Printing things to make sure it's right, and then filling in the formulas. So the fixed effect here, plus or minus 2 standard deviations of the corresponding random effect here. So that should spit everything out nice and neatly for you. Don't have a function for that in R yet, though. Here's some R output. So now we have our 3 random effect variances, the 3 correlations between them. Here's the V matrix that is resulting now. So we don't have that weird half compound symmetry pattern anymore. We see declining variance over time and declining covariance. Would be declining correlations as well if we printed that. So in terms of the overall pattern that these 2 random slopes create, it's still quadratic. So anytime you add a random linear slope of a variable, then variance is heterogeneous as a function of that variable. So if you're adding a random slope for time, then it's heterogeneous across time in a quadratic pattern. But in this case, we've got 2 different random linear slopes, so there's 2 patterns in here. There's quadratically increasing variance between 1 and 2, and then a separate amount of that for 2 to 6. So the pattern is fairly complex. RANOVA in R takes out each of the random effects and tells you what would happen. So it essentially fits the nested models for you that we already did. So we have, if I took out slope 1, 2, the likelihood ratio test would be significant. If I took out slope 2, 6, which is the one I care about here, it's also significant. So looks like we have individual differences in change during each piece. So here are the confidence intervals then that I built. So in my sample, I would expect 95% of the folks at the first occasion to have response times somewhere between 900 milliseconds and 3,000. So quite a bit of variability in how fast people can do this task initially. Their initial rate of change from 1 to 2 is somewhere between negative 660 milliseconds and 300. So not everybody declines at first. On average, there is decline, but there is individual differences in the extent to which that occurs. And if reviewer 3 says, hey, your confidence interval overlaps 0, that means your slope isn't significant, right? What do we tell them?
Some people got slower.
Yeah, the fixed slope has its own significance test for what happens on average. This interval describes individual variation around that. And some people are predicted to go down on average, and some people are predicted to come up. Same thing with the second one. So this is a shallower slope on average, but there are some folks who are predicted to have an increase in response time rather than a decrease. These are real data. Real data are messy. So the code in R, I took the fixed effects and saved those as a data frame, and I took the variance components and saved those as a data frame, and then I asked for those to be printed so I could see where stuff was. So then, for instance, fixed intercept here is row 1, column 1. The first slope is row 2, column 1, so that's where these numbers down here came from. For the variances, the intercept variance is row 1, column 4 of this table, so that's why I have 1, 4 in here. So printing the table shows you where the things are that you need to access for the numbers. That's the utility of that. So I saved each of the values out of those spots and as programming variables or objects in R, and then I stuck them down here in the confidence intervals. So then we get, these are the numbers then that came out. Just more nicely formulated in the book. There, easy peasy. How are we doing? Zoomers, how are we doing? Thumbs?
Can I ask, so for the R code, the data frame basically takes objects that you have saved, but it puts them in like a table for you, and then you can refer to the cells of that table in your subsequent analysis
Yes.
rather than referring to the object directly.
Yeah, so I am not good at working with R objects. Like I never get it right, but I'm much better if it's in some kind of data frame like this. So this may not be strictly needed, but for me it's needed. I think it makes the code more transparent as well. Yep. So yeah, this isn't so bad. So let's look at the other way of doing it then, deviation slope model. So the variables that I'm putting in here is time and slope 2/6. So you can think of it as slope 1/6 for time, but it's the same time variable that we had last week. Question, what can you do to see if the second set of random slopes improves the model? We can do our likelihood ratio test right there. So same thing. As a general operating principle, if you have any research questions about the model for the variance, that's a likelihood ratio test as your answer. Whether you need sources of correlation, whether you need random slopes, whether you need heterogeneity of variance, any questions like that, that's a likelihood ratio test. So the other version of the model then, starting at the same place. So 2 fixed slopes and only a random intercept. Now the constant, fixed constant, back to stata output here, is the same number as before because this is an equivalent version of the first model that we saw. Likewise, the first slope is the same number as before because this becomes not the linear slope all the way through all occasions. It becomes just the slope from 1 to 2 after controlling for this variable. So if you look at the coding scheme and think about unique effects like in a regression context, the fixed effect is always the unique contribution of that predictor after controlling for the other fixed effects in the model. So if I look at this, like there's redundancy here, right? So what orange brings to the table that purple doesn't is just the first part. The unique effect of slope 1/6 becomes just the 1/2 part after you control for this other variable. If purple wasn't in the model, then it would be the linear slope through all occasions, just like we had last week. Likewise, purple is redundant with pink, or orange, excuse me. Purple is redundant. So purple has the unique effect as well, and what it has is the extra part that operates after session 2. So its unique effect becomes the difference in the 2 slopes, or the deviation. So that coefficient is then the 130 that we saw a few minutes ago as the slope difference. So in this model then, we get the change during the first period and the difference in change during the second period. What don't we get?
The exact slope for the second.
The exact slope for the second period, but it's a linear combination. So we can do that by adding together the slope for the first part and the slope deviation gets you to the slope for the second part. So it's 6 of one, half dozen of the other. Here are the estimates. They are the exact same as what they were before. And there is my slope 2 that I got from adding the first slope to the deviation slope. So the 2 solutions then are shown here to compare across. The blue line is the same from either model. The question is how it gets created. So in the first model, I have just the change from 1 to 6, and then just the change from 2 to 6, and so I get the direct slopes for each of those periods. In the second model, because of these becoming unique effects, the interpretation is still the idea that we have, this is the first one here. The idea is that we still have just the slope from 1 to 2 for the first one, but then we have the difference in slope after that instead. So either way you slice it. Question?
So for this model, it's the same estimate regardless of which way you calculate it. Are there any situations where it wouldn't come out the same?
Question, is this always going to be the case that they're an equivalent model? My instincts say yes, but I'm not 100 on that. I think as long as you've set it up, would have like the same intercept, the same 2 slopes, like you should get to the same place. I mean, you could also set it up to where there's a deviation on the first one. Like, and the second one is the one that you're interested in. Like, you could reverse it.
And you could have more than one slope, but could you have more than one deviation?
Yes.
Yes.
Yes, like if you had a three-piece model,
Yeah.
you could have slope, and then the second piece is how that one differs, and then the third one is how that one differs from the second.
From the second. Okay.
Mhm.
So the deviation slope model, the piecewise slope models are not hierarchical, but deviation slope models are hierarchical.
Yes, I would say yes. If you're thinking of slope plus deviation slope as a hierarchy, because the deviation has to deviate from something.
Yeah. Okay.
Otherwise, it would not retain the same interpretation.
Okay.
Yeah.
And if you had like 3 slopes, or rather 1 slope and 2 deviations, then it could be like 2 levels of hierarchy, 3 levels.
Yes, if you had 3 slopes and you had a slope and then a deviation from that and then a deviation from that, then yes, they all stack on top of each other. It's up to you how you code it in terms of what you want to know. But you can be assured that whatever you don't get is a linear combination of what you do get. I think you can get back to all the pieces of information at once.
Okay. That's
Yep. How about some random slopes?
Sure.
Okay, now this is a tricky one. Sure, why not? We're here. I'm contractually obligated to keep talking. I was telling the other class this. It gets worse. When I used to teach summer workshops for ICPSR, they were supposed to be 5 days in a week, 8 hours a day. And it's like the hardest stuff that I teach, like is what the workshops usually are. And I would give people lots of breaks and long lunches and stuff, so it was down to maybe 5 or 6 hours of content in a day. But like at about 2:30,
yeah.
no one is listening to me. Absolutely no one is listening. And back in those days, we had computer labs with big CRT monitors, and so I couldn't even see them not listening to me. I could just like feel it. And it's like, well, you paid, $umpteen-thousand to come to this workshop, and they're paying me $umpteen-thousand to teach it, so I guess I'll just keep talking.
I bet some of them were listening, but they were probably really tired.
Yeah, they're overwhelmed.
Yeah.
They're full. And especially when everything is new at the same time, you get saturated very quickly. So, like, I don't think workshops are actually that useful, and I don't do them as much anymore. I did them for the money, to be clear. That was my primary motivation in those days. I had a mortgage to pay that I couldn't afford. But that's a whole nother story. So I feel you is what I'm saying. I realize that it's 1:30, and we're hitting the limits of the cognition. I understand. Now, this model is sort of weird. On the fixed side, we agree that this is a piecewise model, right? Because I've got a slope and a deviation slope. If I think about these fixed effects and their interpretation. On the random side, though, do I have a piecewise model?
Just linear.
Yeah. I have a random linear time slope. So they don't match because I'm lacking this other slope that would turn this into the change individual difference for just 1 to 2.
Would you ever actually do this in real life?
I would do it as a way to get to the final model to demonstrate that both pieces would need to be random. But if not, then this would imply that change during the entire period differs across people, not just the first part. Like this slope keeps going because it's time that it's multiplying. Question?
Kind of in that vein.
Mhm.
So, say you'd use this model to demonstrate you need both pieces. When you're publishing, do you find that in the final product, people are like, just give me the model that works? Or do
Yes.
They need, okay, so they don't need all the build-up and justification?
Yes, so the question was, in real life, when I write results sections, do I outline each of the steps and what happened at every step? Usually not. It's summarized greatly in a paragraph where I hit the high points, and then you build to the final model. Occasionally, reviewers will want more detail about how you got there, and you can put that kind of thing in a supplement. So, or details about the analysis, I've had to do that lately, where it's like, no, this result section needs to be under this many pages, and it's like, I can't explain it in this many pages. It's like, all right, it's going to a supplement. So that would be a good place to put that kind of like preparatory information that doesn't address research questions. So this thing then, here's the V matrix. Like this is a quadratic pattern of changing variance across all the occasions because it's random time in this step. And we do indeed need that random slope. So we can go ahead and add in the other one. So note the correlation between the two. Very, very high, because time and slope 2.6 are almost the same variable. So I would expect potentially more estimation problems due to that overlap when you're adding random slopes here.
Why are time and slope 2.6 almost the same variable?
Let me
Like,
go
not
back to my
exactly
coding.
the same variable.
It's the first two rows in here. Like these two variables are highly related.
Oh,
So it stands to reason that individual random slopes would be highly related.
okay.
Yep. So the variance components are different in this model because they mean different things. So like this one right here is a different number than what it was before because it refers to individual differences in the deviation, difference in change, as opposed to just the change. So if you wanted to explain why some people react differentially relative to their expected change, that's this variance component. So here is then the full V matrix that has a different pattern and confidence intervals for the difference. So the new one then is right here, the last one. That tells you the expected range of the differences in change between the first slope and the second slope. And here's where the numbers came from to get all of that stuff. So let's see what happens. So on this plot here, I have the best model from the previous example, random quadratic, and then I have the best model from this one, piecewise slopes, either one, 4C in this case. So the right answer with respect to the means is this solid black line. Quadratic is the one that predicts that it's going to come back up. And then, Alex, to your point, my piecewise model predicts that response time would continue declining at the same rate indefinitely, which is dissatisfying and probably not the case.
Right.
Mm-hmm. Now, I could make this second piece quadratic. I mean, this doesn't have to be a linear slope because I have 5 occasions worth of data to work with. I did add a quadratic and it didn't end up being significant, so I reported that in the text as well. On the variance side, though, these are the predicted variances and what would happen if we extended time past what we actually have. Extrapolate. I learned that the other day. It's the right one. So the random quadratic is the one that has a quartic dependence on time, time to the 4th. That's why it goes insane after session 6. The random slope 1, 2, but the fixed part is this like broken function right here, because that one allows individual differences in only the first piece, which allows changing variance in only the first piece, and after that it's constant variance, compound symmetry. Adding the second random linear slope creates a quadratic pattern of changing variance, but it's not quadratic through the whole thing. It's like one part is quadratic and then a separate quadratic pattern after that. So you can see the expected U shape coming back up again for the second piece here. Now, does it fit? We know that having both slopes be random fits better than having them be fixed only, but does it fit? Absolutely. Essentially, how well do these patterns approximate the black line with the squares? That's the last question we have to answer. So we'll do that by 2 more model comparisons. The first one is focusing on the mean side. So I can't do a likelihood ratio test to answer the question, do these piecewise slopes approximate the saturated means well enough, because we're in REML. So instead, I'm going to use a multivariate wall test in which I plug in 3 more parameters to essentially recreate the saturated means. So the point of doing this is not to interpret the model. The point of doing this is to see if these three things as a set help, because if they do, that means my model wasn't good enough already to recreate the saturated means. So I can do that in Stata with a test statement. So I'm asking, hey, can you shut off all three of those slopes and tell me what would happen? And it's like, sure, f of 1.58 with a p-value of 0.2. Good news or bad news?
Wait, what are we testing? There's a significant difference, or sorry, not a significant difference.
Yeah, we're testing the contribution of these three dummy codes. So that these are each indicators as to whether it is session 4 or 5 or 6. And we are doing that because 6 parameters for 6 means should perfectly recreate the means. The question is, do we need these extra ones, or does my model do a good enough job already?
It's not significantly different, so it's okay.
Yeah, it's not significant, which means they didn't help. So my model is good enough. That's the way I would interpret that. On the variance side, because we're in REML, we have to keep the fixed effects constant. So the answer key with respect to what the random slopes are trying to recreate is the unstructured matrix. So that's what I need. I need a version of the model that has my fixed slopes, but then an unstructured matrix. So here's the R code for that. So then here, switching that to unstructured, taking out all the random effects, switching to GLS because you can't do that in Elmer. There's no such thing as an R matrix that's not diagonal in Elmer. And then I had to re-estimate the comparison model using LME so that I could get the likelihood ratio test, and there it is. Survey says test statistic of 15, p-value of 0.3. Good news or bad news?
Good news because it's not significantly different.
Good news. Yeah, it's not worse. So when I first did these tests, I was amused to see that, like, even though this model, theoretically, doesn't make a lot of sense, it fits the data pretty well.
I think it theoretically makes sense.
Well, there's nothing magical about the second, like, session in this type of design, but, I mean, I think it would make more sense in your context, let's put it that way. Yeah, everything is context specific. So yeah, so far this is the winner. But theoretically, it's dissatisfying also because of this linear slope component. We would not expect response time to decline continuously forever. So there's 2 more options that I want to show you, but that will be next week. We have the negative exponential model, which is hard to fit. I only know how to do that in SAS, but I came up with an alternative based on logging time. If you log transform time, that creates what looks to be an exponential curve. And you can add quadratic slopes of log transform time to speed up or slow down that curve. So that will be example 6D that we'll talk about next week. And this one isn't in the book because I hadn't thought of it by then. It will go in the book next time. Assuming I ever fix it. We'll see. I know. All right, questions? So this isn't so bad, right? It's just different ways of making predictors, but fixed effects is what happens on average. Random effects is how people differ in whatever that is. Same principles. All right, then how about we call it a week? Yes. All right, let me know if you need anything. Thanks for being here. Don't blow away. Happy Halloween.
This log transformation is like the answer to algebra.